Hello guys, welcome back to Link's Corner, the place where we share science, learn something new, and make physics feel alive. Today we are diving into one of the most fascinating topics in physics, mechanics, and heat. It's about rotational dynamics. So previously we studied translational motion along a straight line, but now we will focus on rotational motion, where an object spins around an axis. Please look at the image. Yeah, we're seeing a ballerina spinning gracefully on one foot. This is a beautiful example of rotational motion in real life. When she pulls her arm inward, her rotation speed increases. That happens because her moment of inertia change. This principle also applies in many engineering systems: turbines, car wheels, electric motors, even satellites maintaining their orientation in space. So, in this chapter, we will explore how force causes rotation, how torque act as the rotational counterpart of force, and how energy and momentum appear in rotational systems. This topic is fundamental for engineering students because almost every machine or industrial system involves rotating components. Now, let's move into the core part of rotational dynamics, understanding the rotational variables. In translational motion, we have quantities like displacement, velocity, acceleration, and force. In rotational motion, we also have their counterparts, quantities like torque and rotational inertia. We are now looking at rotation, where an object spins around a fixed axis. Interestingly, the same laws that apply to linear motion also apply here. We just express them with rotational analogs. Force becomes torque, and mass becomes moment of inertia. Next, we define what we mean by a rigid body. That a solid object that rotates as one piece, with all parts looped together. Think about a car wheel, an electric fan, or a brake disc. All parts rotate together as one unit. In this topic, we will focus only on rotation about a fixed axis. That means the axis of rotation doesn't move. We exclude more complex systems like the sun, where gas layers rotate differently, or a rolling bowling ball, where both rotation and translation happen simultaneously. This fixed axis is what we call the axis of rotation. The angular position of an object is its orientation relative to some reference line. We usually measure it from a reference direction called the zero angular positions. And as shown in the diagram, when an object rotates counterclockwise, that is considered the positive direction. Next, we will discuss angular positions units, the unit used to measure rotational position. In linear motion, we use meters for distance. In rotational motion, we use radians to measure angles. Now, what is a radian exactly? A radian is defined as the angle subtend when the arc length or s is equal to the radius r. Mathematically, we have theta equals to s per r. Since both s and r are measured in meters, radians are dimensionless. They are just a ratio. One full rotations correspond to 360 degree, which equals 2p radian. So when a wheel makes one complete revolution, it rotates through 2p radians. Important note, we do not reset the angle theta to 0 after each full rotations. If the object keeps spinning, we allow theta to keep increasing. That is crucial when calculating angular velocity and angular accelerations. Now, let's define angular displacement, which is simply the change in angular position. Delta theta equals to theta 2 minus theta 1. It tells us how much and in which direction the object has rotated. And here is the sign convention. A counterclockwise rotation is positive, while a clockwise rotation is negative. That's why we sometimes say clocks are negative. So when you look at spinning fan or the motor of a car, its rotation direction determines the sign of its angular displacement. Now we move on to an essential concept in rotational motion. We have angular velocity. In linear motion, we define velocity as v delta x per delta t. In rotational motion, we have a similar idea, but we replace linear displacement x with angular displacement theta. So the average angular velocity is defined as omega average equals to delta, theta 2 minus theta 1 per T2 minus T1 equals to delta theta per delta T. Okay, this quantity tells us how fast an object changes its angular position over time. For example, if a fan rotates through 10 radians in 2 seconds, its average angular velocity is 5 radians per second. To find the velocity at a specific instant, not an average, we take the limit as delta t approach 0. That gives us the instantaneous angular velocity. And we have omega equals to limit delta t approach 0, delta theta per delta t equals to d theta per dt. It represents the rate of change of angular position at a given moment in time. For a rigid body, this equation applies to every point on the body because all parts of a rigid object rotate together as one solid unit. So a wheel, a gear, or a turbine blade all share the same angular velocity. The magnitude of this velocity is called angular speed. The direction convention remains the same. Counterclockwise is positive, clockwise is negative. A practical example in engines, when you read 3000 rpm on a car tachometer, it means engine shaft completes 3000 revolutions per minute, which is about 314 radian per second. So the concept of angular velocity directly describes how fast something spins in the real system. Now that we have defined angular velocity, let's move on to the next concept. We have angular accelerations. Conceptually, it's same as linear acceleration, just in rotational form. In linear motion, acceleration is a equals to delta v per delta t. In rotational motion, we replace linear velocity v with angular velocity omega. So the average angular acceleration is defined as alpha average equals to omega 2 minus omega 1 per t2 minus t1 equals to delta omega delta per delta t. This represents how fast the angular velocity changes over time. For example, if a motor's angular velocity increases from 100 radian per second to 140 radian per second in 2 seconds, its angular acceleration is 20 radian per second square. To find the value at a specific instant, we take the limit as delta t approach 0. So alpha equals to lim delta t approach 0 delta omega per delta t equals to d omega per dt. That is the instantaneous angular accelerations. If the object is a rigid body, this equation applies to every point on the object because all parts of the body rotate together with the same angular acceleration. To determine the direction, we use the right-hand rule. If the rotation is counterclockwise, the thumb of your right hand points outward from the page. That is the direction of the angular velocity and acceleration vectors. If it rotates clockwise, the vector points into the page. In summary, when an object speeds up in the positive or counterclockwise direction, its angular acceleration is positive. When it slows down, the angular acceleration is negative. This concept will be very useful later when we connect torques and angular accelerations, the essence of rotational dynamics. Alright, let's check another topic, another subtopic, the rotation with constant angular acceleration, one of the most useful case in rotational dynamics. When the angular acceleration is constant, the motions follows equations that are exactly the same in form as the equation of uniformly accelerated linear motion. So the key idea, the same motion equation apply, we just replace linear quantities with angular quantities. So we make the following substitution: displacement x with angular position theta, velocity v to angular velocity omega, acceleration a to angular acceleration alpha. Now, at the table on the slide, on the left side are familiar linear equations, yeah, and on the right side are their rotational counterparts. Okay, the first equation we have v equals to v0 plus at, and the angular equations is omega equals to omega 0 plus alpha t. This shows how angular velocity increases over time if there is angular acceleration, like when an electric motor starts spinning faster after being powered on. Okay, so yeah, this is the sum of the equation in linear equation and angular equations. So if you already understand linear kinematic, rotational motion will feel like its spinning version. In engineering, this principle has many applications. For example, in braking systems, we can calculate the negative angular acceleration needed to bring a wheel to rest in a given time. And in electric motors, we can determine the torque required to reach a certain speed within a few seconds. So, this topic bridges what you already know in translational motion to real-world rotational system used in machine. Okay, now let's discuss how linear motion and rotational motion are related. This is a key idea because every point on a rotating body actually moves in a circular path, which means it also has linear motion. And shown in the figure at a point P here, a rotating body travels in a circle centered on the rotation axis. The distance from the point to the axis is called r, the perpendicular distance from the rotational axis. The relationship between linear and angular quantities is based on this R value. Let's go through them one by one. The first one we have position. The R length traveled by the point is S equals to theta r. The larger the angular displacement or the greater the radius, the larger the linear distance. For example, the other edge of a car tire travel farther than point near the hub. The second one, we have speed. The connection between linear and angular speed is v equals to omega r. Every point on a rigid body has the same angular velocity, but different linear velocities depending on their distance from the axis. Think of a fan blade. The tip moves much faster than the inner part near the center. Okay, next we have period. One full revolution corresponds to 2p radians, so t equals to 2p per omega. The faster the angular velocity, the shorter the period, just like smaller gears spinning faster in a gearbox. Then we have tangential acceleration. When angular velocity change, each point has a tangential acceleration. So we have a t or a tangential equals to alpha r. This acts along the tangent to the circle and depends on both angular acceleration and radius. Finally, we have radial or centripetal acceleration. Each point also experiences an inward acceleration. So AR or a radial acceleration equals to v squared per r equals to omega squared r. This keeps that point moving in a circle instead of flying outward. It's the same concept that keeps a tire's rubber moving in a circular path or the rotor blades of a motor intact under high rotation speed. In summary, linear and angular quantities are connected through the radius of rotations. The farther a point is from the axis, the larger its linear velocity and acceleration. Now, let's discuss one of the most important ideas in rotational motion. We have the kinetic energy of rotation. In linear motion, the kinetic energy is given by K equals to half mv squared. For rotational motion, we apply the same idea, but each particle in a rotating body may have a different linear velocity depending on its distance from the rotation axis. For a rigid body, we can think of it as composed of many small particles. Each particle I has a mass mi, a distance ri from the axis, and a linear speed vi. So the total kinetic energy is the sum of all particle energy. And then we have this formula. Since every particle rotates with the same angular velocity omega, we can write v I equals to omega Ri. Substituting to the first equation, now we have this formula. The term inside the parenthesis, this one, is called the moment of inertia or I. So we have moment inertia, these equations, and the rotational kinetic energy becomes K equals to of I omega squared. Moment of inertia plays the same role in rotation as mass does in linear motion. While mass measures how hard it is to change linear velocity, moment of inertia measure how hard it is to change rotational motion. At the figure, we have two long roads. A long road is easy to rotate about its central axis, this one, but much harder to rotate about an axis perpendicular to its length. That is because the distribution of mass relative to the axis, the r values, are different. So the moment of inertia is different. That's why we must always specify the axis of rotation when giving I. It's not just about the shape or mass, it's about how the mass is distributed relative to the axis. In short, rotational inertia tells us how resistant an object is to change in its rotation. A flywheel, for instance, has a large moment of inertia to maintain steady rotation. It resists change in angular speed. Now that we understand what the moment of inertia I represents, the resistance of rotational motion, let's see how we can calculate it. For a continuous body, we use I equals to integral r squared dm. This means we sum up every small mass element dm multiplied by the square of its distance r from the rotation axis. So, the farther the mass is from the axis, the greater its contribution to the total moment of inertia. In principle, we can always use this formula, but mo for most engineering cases, the moment of inertia for common shapes have already been calculated, as shown in the table. For thin hoop or ring, solid cylinder or disc, thin rod, and the others, we already we have uh, the calculations of moment of inertia. Clearly, the axis of rotation plays a major role in determining the value of I. Now, let's talk about the parallel axis theorem. If we know the moment of inertia about an axis through the center of mass, I center of mass, then the moment of inertia about any axis parallel to everything and a distance h away is I equals to I center of mass plus mh squared. Be careful, the axis must be parallel and one must pass through the center of mass. This theorem doesn't work for arbitrary axis. Okay? For example, if a solid disk rotates about nh instead of its center, we can find its moment of inertia as I equals to half mr squared plus mr squared equals to 3 per 2 mr squared. So the farther the axis is from the center of mass, the harder it is to rotate the object. In summary, moment of inertia depends not just on how much there is, but on how that mass is distributed relative to the axis of rotation. Now, we move on to the one of the most fundamental ideas in rotational dynamics, torque. In linear motion, a force causes translation. In rotational motion, torque is the quantity that causes rotation. So, torque is basically the rotational effect of a force. Its magnitude depends on two key factors: the magnitude of the applied force and the perpendicular distance from the axis of rotation. Mathematically, we write torque R F sin theta, where r is the perpendicular distance from the rotation axis to the line of axis of the force, F is the applied force, and theta is the angle between the force and the lever arm. If the force is applied perpendicular to the lever arm, the torque is maximum. If the force is applied along the arm or parallel, the torque is zero. Think about opening a door. If you push near the hinge, the door barely moves. But if you push at the other edge of the handle, the door rotates easily because the moment arm R is larger. The line of action is the extended line along the direction of the force, and the moment arm is the perpendicular distance from this line to the rotation axis. And the unit of torque is Newton meter. Even though 1 joule equals to 1 Newton meter, torque is not energy because it doesn't represent work done, but rather the tendency to rotate. We also define the direction of torque using the sign convention. Counterclockwise torques are positive, clockwise torques are negative. When multiple forces act on a body, the net torque or resultant torque is simply the sum of all individual torques. So, how that goes to yeah, these equations. These net torques determine whether the object speeds up, slow down, or change its direction of rotation. And then we arrive at one of the most fundamental principles in physics, Newton's second law, that this time applied to rotational motion. In linear motion, we have F equals to ma, meaning that a net force produces linear acceleration. For rotational motion, we simply replace linear quantities with rotational ones. Using this one. This is the rotational form of Newton's second law. It tells us that net torque plays the role of force, moment of inertia plays the role of mass, and angular acceleration plays the role of linear acceleration. In other words, torque causes angular acceleration, just a force causes linear acceleration. In the diagram, a rigid rod can rotate about an axis at a point O. A force F is applied at the end of the rod, a distance r from the axis. The tangential component of this force Ft is what actually produces a torque, and that torque generates the angular acceleration alpha of the rod. If we want to make something rotate faster, there are two ways. First one, apply a larger force, or second one, apply the force farther from the axis, increase the level arm R. However, if the object has a large moment of inertia, meaning its mass is distributed far from the axis, it's much harder to rotate. So even a big torque will produce only a small angular acceleration. This is why a small motor can quickly spin a fan, small I, large alpha. But a huge turbine requires enormous torque to start spinning, large I, small alpha. So the key takeaway here is torques produce angular accelerations. The larger the net torque, the greater the change in rotational speed, provided the moment of inertia remains constant. And finally, we reach the final part of rotational dynamic, the relationship between work and rotational kinetic energy. From linear motion, we already know that W work equals to delta K, which means the work done by a force equals the change in kinetic energy. In rotational motion, the same principle applies but using rotational quantities. This is called the rotational work kinetic energy theorem. So we have this equation. So the work done by a torque equals the change in rotational kinetic energy. We can calculate work in rotation using W or work equals to integral theta I to theta F torque d theta. This means if a torque acts through an angular displacement, the total work is the area under the torque versus theta curve. For constant torques, this simplifies to work equals to torque theta F minus theta I, which directly mirrors W equals to F xf minus xi from linear motion. So torque is the rotational analog of force and angular displacement is the rotational analog of linear displacement. At the table, this is summary the corresponding quantities between translational and rotation motion. We have position and in rotation we have angular position theta. Velocity, angular velocity. Acceleration, angular acceleration. Mass, moment of inertia. Force, to torque, and work, to this one, torque d theta. Kinetic energy, half I omega square. Every linear motion equation has a rotational equivalent. That is the beauty of classical mechanics. The patterns are universal. Finally, we can relate to work from watt to power using P equals to dW per dt equals to torque omega. So the power output of rotating system equals torque times angular velocity. For example, in an engine, the mechanical power is produced by the torque of the crankshaft times its rotational speed or RPM. That's why every engine specification lists both torque, Newton meter, and power, watt or horsepower. They are directly related through this equation. So in summary, force causes linear acceleration, torque causes angular acceleration, linear kinetic energy depends on mass and velocity. Rotational kinetic energy depends on moment of inertia and angular velocity. So, yeah, that is for today, guys. We explore how rotational dynamic explain the stability of spinning object from a simple tops and to work and rotational kinetic energy. Remember, physics is not just about number and formula. It's about understanding how the universe spins, moves, and stay in balance. Thanks for watching and see you in the next video.